Hello, welcome to Evaluating Limits Without Graphs. This is our second lesson on limits, and we are going to be using knowledge about our parent functions and other functions we've encountered in this lesson. So to start off with, number one has the limit as x approaches -3 for our function x. Now, x is pretty easy to describe. Remember, when you see the limit notation, so here's our limit notation in blue, and the function in yellow, that function in yellow can be represented on a graph. It is the relationship y equals x, f of x equals x. So it's not just telling you something non-specific, it's very specific with the function it gives. So if that function is x, what is happening to the y values when x approaches -3 on the function y equals x? Well, in my head, I know that the graph of y equals x looks like that. It's that pink function. And I know what the output is. I know what the y values are doing on y equals x. So I can just respond with that. I've got what's happening at -3. That is -3. So here, this is called direct evaluation. So we can directly evaluate this limit because it's a line. Because a linear function has no discontinuities. We get into trouble when we have a discontinuity to look at. So the next question is, what's the limit as x approaches 3 for this function? Well, this is a polynomial, this is a cubic, and it's facing down. Woo, it's facing down. We don't need to graph it. You need to think, is this function continuous? Does it have any discontinuities? If there aren't, then we need to directly evaluate. There's nothing special we have to do. So we'll just pop in 3 into this function because that's where all our y values are going to at 3. And this is going to be equal to 3. Now for these 3 and 4, and I believe 5 and 6 as well, we need to remember a couple things about rational functions. And I wanted to include this graph, just so you can remember the shape that these rational functions take. In this rational function, we have factors. It's in factored form. And I want to highlight this group of factors in particular. If there is the same factor in the numerator and the denominator, then that represents a whole. We have a hole in the graph. So we can look at that hole at -1, because remember, if you're solving for when x equals 0, so x plus 1, when that's 0, x is equal to -1, we have a hole at -1 because if we were to plug in -1 into this factor, so the same factor that's in our equation, f of x, then we would have a 0 in our denominator, which is not allowed and would produce an undefined value in our graph. But because we have the same factor in our numerator, then that just produces a whole and it doesn't completely skew the graph. What will skew the graph considerably is if there is not the same factor. So if lone factor in the denominator this produces a vertical asymptote or a non-removable discontinuity. I'm going to abbreviate a few things there. So our vertical asymptote at 3 happens when our factor is x minus 3. So there are a couple of things we can answer. What is the limit as x approaches 3 of our function? And you would say, well, because that produces a vertical asymptote, then that is d and e. Our left and right sides do not equal each other. But what if I asked you, what is the limit? Let me ask that right here. The limit as x approaches -1. And so you would have to tell me what y value we're approaching from the left and the right of -1. Now, I've already shown what the point is. As we approach -1, our y value is -1/4. But the way to determine that is just remove the whole. So we will remove, that's why we call it a removable discontinuity. So we'll take what is f of -1 of 1 over x minus 3, and that will give us -1/4. So that's how we get our answer of -1/4. We evaluate 1 over -1 minus 3 will give us -1/4. So we have a couple different ways to approach these rational functions that we see down here. We're going to factor them and then decide what to do with those factors. So for number 3, what is our factorization? I've got x plus 3 over x plus 3, x plus 2. And I want to know what's happening when the limit approaches -2. Well, this is the lone factor. It does not have a pair. So based on what we know the pattern to be on these rational functions, then this is d and e. So we do not need a graph of this because all of these follow the same pattern. Number 4, we'll factor x minus 4. The negative can stay up there. It doesn't change our factorization. X minus 4, x minus 3. This means we will have a whole at 4, which is what we're being asked about, because it says what's the limit as x approaches 4. So this is a whole. So I have to remove the whole and evaluate at 4. So I've got -1 over 1, that's -1. Yay! Alright, so with 5, you're being asked what is the limit as x approaches -1. This already looks a little shady because there's only one factor in the denominator. sorry, hold on. What up? There we go. But thankfully it matches. So we have a hole. Those can be removed, and I'll evaluate. So this is x is -1 minus 4. I've got -5. And then lastly, for our rational function examples, we've got this one where x plus 4 over x plus 4 x plus 5 plus 1 is our factorization. And we can already tell this is going to be a whole, so we'll have, I'll just evaluate real quick, 1 over -3. Yay! I'm going to change this one just to ask the same, with the same function, to ask a different question. What happens if I ask you, as x approaches, let's just say 3, is 3 on this function, the x plus 4 over x plus 4 over x plus 1, even a problem? There's no problem, because 3 is on a part of the graph that is not represented by a hole or a vertical asymptote. So we can just evaluate. This is direct evaluation. So we'll plug in 3 to get 1 over 4. Cool. Now with these final examples, 7 is piecewise, 8 is a piecewise, and you're being asked about the evaluation of it at 2. So if we look at each piece individually, this piece is linear, this piece is linear. Okay, cool. So this looks like direct evaluation. As x approaches 2 from the left, our limit is going to be -2 times 2 plus 9, which is 5. As x approaches 2 from the right, our limit is going to be 2 minus 6. That's -4. So this is a case where the limit does not exist, because it does not exist at 2. In this example, same deal. We'll look at the left and right sides, or do we? This is the left-sided limit. So which of these equations looks at the left and right side? Well, if x is less than -2, then this is the left side of our equation. And I'll just evaluate on the left side of -2 to get -2 squared, which is -4. Alright, so there you have it. I'll see you guys later. Bye.